Good morning, everyone. We'll consider two major topics today. The first topic is technological surges of the Industrial Revolution. And the second topic is two major engineering traditions and their implications for technological progress. After the lecture, I'll answer questions and hopefully we'll have some discussion. The first part of this lecture is 5 surges of the Industrial Revolution. In this part of the lecture, we're going to follow ideas of several very prominent economists: Kondratiev, Schumpeter, Freeman, and Perez. Nikolai Kondratiev was first to discover long-term oscillations in economic activity. The period of such oscillation is around 50 years. He actually was executed back in Soviet Union, but Joseph Schumpeter found and published his works. He extended this theory, further pointing to so-called creative destruction of economic forces. For us engineers, the most interesting approach is given by Carlota Perez. She reinterpreted these oscillations of economic activities as technico-economic surges. So such surges involve gestation, which is a latent period in technological development, which is not particularly visible, and then a big bang event when a particular technology becomes clearly visible, which is followed by eruption and frenzy. Eruption is very fast exponential development of this technology, and frenzy indicates a general trend of markets to overshoot. This creates a bubble. Financial bubble usually collapses, inducing a market correction, which is again followed by another period of growth, more gradual growth, but more synergetic and more productive. Finally, the technological wave achieves its maturity, and any further development becomes very difficult. At some stage, this technological wave is replaced by another wave. Here you can compare technological wave of Kondratiev, which is a mere oscillation in economic activity, with interpretation given by Carlota Perez, where the major driving force of economic change is technological innovation, technological progress. As you understand, this perspective of Carlota Perez is most relevant to our engineering interest. We are interested in technology. Each technological surge is not just a technological surge, according to Carlota Perez, but a change in technico-economic paradigm, which would involve not only technological shifts and developments, but also some economic and organizational changes. According to Carlota Perez, we had 5 industrial surges. These 5 industrial surges of the industrial revolutions, they completely changed our world. The first 2 surges were led by the United Kingdom and usually are called the first industrial revolution. In the same way, surge number 3 and surge number 4, they also have some similarities. They were led by United States and Germany, and usually unified into the second industrial revolution. Finally, we have post-war industrial surge, which is usually termed as a third industrial revolution. As you can see, each of these surges is associated with development of a certain groups of technologies, certain clusters of technologies. The fourth surge was interrupted by world wars, which represent a very significant disturbance of economic and technological development. Certain technologies were accelerated, these technologies which related to war efforts, and the development of some technologies was delayed. So we might have different dating of technological surges. And finally, it seems to be the case that we now have yet another technological surge, surge number 6, and it can be considered to be the second phase of the third industrial revolution, or many people believe that we are facing a very significant change, which is called technological revolution 4.0. Just yet another industrial revolution. While we're going to consider each technological surge and each industrial revolution in detail, this table lists all major facts about technological surges as they were introduced by Carlota Perez. Generally, economists of different persuasion can never agree on how important technological development is and what exact dates associated with each technological wave or technological surge. But we use interpretations and dates as they are nominated by Carlota Perez. I think they're most accurate and they're most relevant to engineering perspective. So this table indicates major technological changes in this column, nominates leading countries which led a particular technological surge, and indicates different phases of each technological cycle, and nominates important dates and key events. At the bottom of this table, I took the liberty of adding some possible further development. It's yet another technological surge. It's not very clear if it's indeed happening or not. I've heard some opinion of Carlota Perez herself a couple of years ago, and she said that we are still at the end of the 5th industrial surge. We are still somewhere here. Whether we have a new industrial surge or not can be determined only after 10-20 years, when economic impact of technological change will become visible. And now to the first industrial revolution. During this revolution, science and technology developed in parallel without much influence on each other. Science was too weak to provide any specific advice to engineering, and engineering wasn't much interested in science. So the first industrial revolution was led by United Kingdom, which overtook France and Netherlands, and later on followed by America and other European countries as well. So we can distinguish 2 industrial surges during the first industrial revolution. And the first surge was characterized by extensive construction of transportation lines, and canals were used for this purpose because railways were not known at that stage. Mechanization of textile industry with a dramatic increase of productivity. and Watt engine is another symbol of the first industrial surge. It's a low pressure engine which wasn't particularly efficient. Once Watt's patent expired at the turn of the century, high pressure engines were introduced, but they had limited use as most of the energy was sourced from hydro and sources in wind. This energy was used in factories. The second surge, it completed changes which were initiated during the first surge, and the second surge was very instrumental in extending steam power to different areas. Steam power was used in factories on a large scale, on railways. It was development and construction railways. In the same way as construction of canals caused canal mania and financial bubble, which later burst, construction of railways created just another bubble, financial bubble, but large territory of Britain was covered by railways relatively quickly. Wide use of steam involved navy and ships, ports. City gas, of course, was introduced during the second stage. Telegraph, you can see city gas here, and it's a rocket, one of the very first steam locomotives which won the prize and became one of the first locomotives used for the transportation of passengers and goods. The second industrial revolution can be characterized by more close interaction of engineering and science. New areas developed, such as thermodynamics, physics of electromagnetic processes. All these areas were of interest for engineering and were used in development of new technologies. United Kingdom started to lose its leadership, industrial leadership, because it performed quite well in all the industries, but not so well in the emerging new technologies. Germany was especially strong in chemical industry, and United States started to overtake Britain using developing different applications of electricity. So we can see some newest bulbs and electric engine. This surge saw very large scale construction using new steel technologies. Finally, we should mention some first undergrounds in London and possibly in New York. Of course, just communication. Telephone was invented and used over many years as one of the major tools of communication. Internal combustion engine was invented during the third surge. Once electricity was used, we could build tall buildings using lifts. So cities became higher and higher. But many of technological changes were not completed during the third surge, and completion falls into the fourth surge, such as wide use of internal combustion engines in cars, widespread use of cars, full-scale petrochemical industry, airplanes, airports. Again, initially they used internal combustion engines. Introduction of refrigeration. And finally, of course, while electricity started, effective use of electricity started in surge 3, creation of national-wide grids, national-wide electric grids was completed during surge 4. Again, surge 4 was interrupted by world wars. That's why dating different technological development becomes a little bit more difficult and maybe just a little bit more ambiguous. The post-war industrial surge, which is also called the Third Industrial Revolution, is characterized by emergence of a strong symbiosis between science and engineering. It was to some extent stimulated by significant scientific discoveries of the 20th century, and to some extent to a strong competition between the United States and Soviet Union. However, after economic collapse of the USSR, the trend was reversed, and industrialized countries moved towards more practical interpretation of engineering. Let us consider major components, major periods of the Third Industrial Revolution. Just after the war, this period was characterized by completion of some transformations which have started before the war, but were not completed. For example, its introduction of diesel on railways, mass-scale introduction and replacement of steam locomotives by diesel locomotives, introduction of TV. But in some respects, it was a beginning of a new technological development, which was induced and stimulated by the war efforts. And this would be development of space technologies and also various application of nuclear technology and nuclear engineering. The actual Surge 5 is considered to be initiated in 1970s, and it's associated with development of digital and computer technologies. It also brought a new wave of digital communications, internet, and you might recall this economic bubble, which is dot-com bubble, which results in usually in a bubble burst and correction, and more gradual development in early 2000s. In some way, development of computer technologies and especially internet did not affect major industries at that stage. So we should expect that these changes in communications would have a profound effect on at least some of the industries. And that's probably is going to be associated with yet another technological surge, Surge 6, which might have just started. We don't know it yet. So this sixth surge, which sometimes is referred to as Industrial Revolution 4.0, is associated with commercial space, electrical cars, wide application of renewable energy, nanotechnology, genetic engineering, but of course, artificial intelligence, and also a general development of new approaches. Each technological surge is not just a technological change, it's also a change in organizational principles. And what is emerging currently is a new forms of organization, new and more efficient, more flexible, more innovative forms of organization, which involve some network type structures. So control over such complex structures such as network swarms, studies and control of systemic complexity is another technological achievement, which is expected to be associated with the next technological surge. You probably are familiar with the product life cycle right here, especially if you had some management courses. The product goes through several phases: introduction, growth, maturity, and then decline. But here we speak about technological life cycle, and technological life cycle is related not to a single product, but to a group of products which form a particular technology, or even to a group of technologies, a cluster of technologies. It had conceptual similarities with product life cycle. Initially, we have a Big Bang event when it's clear the technology becomes viable, and it involves a clear demonstration of this viability, which is followed by usually exponential growth, market overheating, correction, and then more productive but gradual growth after the settlement of this overheated market. Finally, it reaches maturity and exists in mature states where improvements are small and incremental. And finally, this technology probably goes into obsolete stage and is replaced by something else, by a new generation of technologies. It's interesting that this duration here for a particular technology may last not necessarily one surge, but might involve, say, 2 technological surges. For example, cars with internal combustion engines, they existed at least over two technological surges. Let us examine technological life cycle in greater detail. First of all, we have a domain of unknown, where scientific research is conducted. Some discoveries can be used to produce new technologies. This is the domain of emerging technologies. They gradually transformed into existing technologies, which reach maturity and then go into decline and becoming obsolete. So these are different phases, different phases of technological cycle. And these different phases are associated with different sets of skills which are required at these stages. Most important at initial stages of emerging of new technologies is ingenuity, dedication, and later on it comes to strategic decision making. And finally, as technologies become mature, we speak about traditional management. At the end, it's simply a low-cost labor trying to use existing technologies and reduce the production cost. Now, let us try to answer the question why technological progress arrives in form of these waves or surges. We're going to use a little bit of help from Harvard Atlas of Economic Complexity. And this graph here represents connections between different industries. Each node is a specific industry producing a certain set of products. And as you can see, these connections, they form clusters, industrial clusters. For example, this cluster corresponds to textile industries. This cluster corresponds to construction. Industries are not autonomous from each other. They have connections. They produce some products which are consumed by other industries. Because of this, when we have a technological progress, it usually arrives in development, not a single industry, but a cluster of industry. And such development of industrial clusters, it results in an economic surge, an economic wave, which economists have noticed and recognized. In our group, we have conducted some analysis of clustering structure of this graph, representing connections between different industries. And this was based on random walks on this graph. By the way, we're going to study similar models later in this course. So as a result of this analysis, we formally determined major clusters, major industrial clusters, and we're able to associate each cluster with a certain characteristic formation time. So these clusters here at the top are easier to create because they have relatively small formation time and very tight relationship between different elements of the cluster. These clusters, industrial clusters at the bottom, are most difficult to create. You might notice that this sequence of industrial clusters, which represents the modern structure of industries, modern relationships between industries, it roughly corresponds to historical patterns of industrial revolution. Not exactly the same, but there is a significant resemblance. That's probably because some connections between industries, they are fundamental, and then they tend to persist. They tend to persist through time. Countries which industrialized relatively recently, such as China, they generally went through the same sequence of developing industrial clusters, which strongly resembles the sequence of development during historical stages of the Industrial Revolution. The second part of the lecture is about two major engineering traditions, and most importantly, about their implications for technological progress. So why we need to consider these two different engineering traditions? First of all, I need to mention that dramatic failures of the 20th century, that of Nazi Germany and Communist Soviet Union, these failures were not related to technological development. These two regimes were terrible regimes, of course, but technological stagnation was not one of their problems. That's why their failures are not of particular interest for us engineers. And consideration of these issues should be left to politicians, political scientists, economists. But the case of Britain is of particular interest for us. During the times of the Second Industrial Revolution, Britain was at the zenith of its economic and political powers. It had a very well-established, stable political system, very progressive, ensuring some basic freedoms. British culture was and is attractive, and British science was particularly strong. Yet, despite all of these priorities, Britain essentially lost competition in developing new technologies to other countries. Let us examine this old British engineering tradition, which has a direct relevance to this event and is of particular interest for us engineers. So, who were these people? First British engineers who introduced a series of inventions which changed United Kingdom, industrialized United Kingdom, and ultimately changed the whole world. These were very talented, creative people with superior personal qualities, entrepreneurial, but at the same time, they didn't have any specific engineering education. They just had some practical experience. In modern terms, they would be considered as technicians, able, talented technicians, but just technicians. And that's how they were seen and treated during the times of the First and the Second Industrial Revolution. A good example of a British engineer is Richard Trevithick, a very tall, strong-willed as well individual. He invented first locomotives, quite small devices, but they were working devices. And later on, these ideas and his inventions were used to develop the whole railway industry. He didn't have any specific engineering education. He was a very practical person. Let us compare this British tradition to French tradition. French traditions received the best possible education in the country. They learn mathematics, science. Quality of their education is remarkable, but it can be argued that French engineers lacked practical skills. They tend to occupy government positions instead of being more independent and entrepreneurial. They might be insufficiently inventive. This difference between British and French perception towards engineers probably can be noticed in how polytechnic institutions are seen in these countries. In United Kingdom, polytechnics are inferior institutions which provide very basic education, and the level of this education is well below that of universities. In France, these are the best institutions, most prestigious institutions. Their graduates occupy very prominent positions in engineering, in business, in politics, and their status is much higher than that of the ordinary French universities. A good example of French engineer is Sadi Carnot. He invented not just a particular device, he invented a principle. And this principle applies to every engine. And later on, 50 years afterwards, this principle, which we call now Carnot cycle, was used to develop one of the most fundamental laws of nature, the second law of thermodynamics. If you speak about these two traditions, these are old French and old British traditions. Later on, these traditions were merged, first by Germany, which unified British practicality with the strength of French education. And this trend was followed by the United States. Yet, some cultural stereotypes in understanding what engineering profession entails to involve tend to persist through centuries and do have some implications even now. So which one of these traditions appears to be most effective in implementing technological progress? If we speak about the first industrial revolution, it clearly was British tradition, which was extremely effective. Britain overtook its major rival, France, and was the first nation to industrialize. Situation has changed during the second industrial revolution. It appeared that practical British engineers did not have enough education to deal with more complex and more science-related technologies which emerged during this industrial revolution. Electrical industry, chemical industry, they required quite a bit of scientific knowledge. At the same time, Germany and United States, they implemented a combined approach to engineering, which unified British practicality with a good, solid scientific French education. And these countries became, step by step, became leading countries in these new technologies. Again, British science was quite strong. And we cannot say that it's British science which failed to be adequate during the time of the Second Industrial Revolution. But engineering and science were very much separated. It was an unbridgeable gap between engineering and science in Britain. And it was one of the major causes of British rather average performance in the Second Industrial Revolution. As you can see, United Kingdom was overtaken by the United States and Germany. Some institutions in Germany which pioneered this unified approach which combined fundamental and applied science, they became the best institutions in the world. And a good example is the Göttingen University. Again, after the Second World War, the strong competition in technology between America and USSR created this merger between science and engineering, effective symbiosis. And this very strong scientific-based education was very instrumental in this competition. But after collapse of the USSR situation, to some extent reversed. Now we are entering another technological competition, this time with China. And it's very clear that educational systems, engineering education around the world will respond to this competition. The modern engineering tradition is, of course, quite different from the old British and the old French engineering traditions which existed during the times of the First and the Second Industrial Revolutions. Modern engineering went through many changes and many reforms. It's interesting to note that some of these reforms, which quite often were conducted by very prominent and very intelligent people, such as Prince Albert in the middle of 19th century, or Winston Churchill in the middle of 20th century, were in fact unsuccessful or partially unsuccessful. At the same time in Australia, the reforms conducted by then the Prime Minister of Australia, Robert Menzies, were very well planned, very well thought, and ultimately very successful. Modern Australian strength in research and education is the major outcome of these reforms. Towards the end of the 20th century, situation has changed a little bit, and governments introduced another series of reforms with a very positive and very important goal of involving more population in the higher education. While this goal generally has been achieved, the reforms conducted in Australia and other countries, in Australia they're called the Dawkins Revolution, they had some aspects which were controversial and politically driven. These aspects resulted in a partial decline of academic standards. But the situation is changed, has been changed again. In the last decade, governments at different levels started to prepare their populations for yet another round of technological competition. And they started quite correctly to introduce some changes initially at the school level. These changes involve selective schools or academies with emphasis on STEM subjects, with deeper education in mathematics and mathematics-related subjects, more rigorous individual assessment. And it seems that universities around the world will need to follow these changes. Let us try to summarize the main points. The coming decades are likely to be dominated by yet another wave of technological competition. And generally, technological progress is not guaranteed by advanced economic development or economic prosperity. It requires special concentrated efforts, especially in technological education. And you may notice this new emphasis, at least at school level, on technological education and mathematics. And that's exactly what we're trying to do in this course. Learn some more advanced forms of mathematics related to overall development of technology. Another point is that we had an internet revolution. It dramatically changed how we communicate with each other, and it's likely to result in yet another acceleration of technological progress. Of course, we will have some benefits from this, but there are some difficulties that and pressures that we're going to experience. First of all, previously, people tend to be educated in a certain specialized area and continue their specialized profession for the duration of their professional lives. This might change, and people will need to learn more or relearn, adjust, adapt. So loss of job security is likely to be a new feature, even for people who are professionals, who have professional knowledge. In this context, this broader systems education might be of a significant help.